Hello, welcome back to SCI Teach. This is a chemistry revision continuation from where we stopped. So in the previous video we did SS1 chemistry revision, SS2, which is where we are right now. And we've done the first and the second terms, and this is the third term work we're going to handle now to finalize class 11, grade 11, SS2 work. So we're going to look at redox reactions, electrolysis, electrode potential, and alkanols. So go along with me as I revisit all these topics to refresh your memory and to help you prepare for your examinations. Don't forget to subscribe to this channel so that you will get educative resources that will help you in your academic endeavors. Alright, so subscribe, like the video, share to your friends and classmates who are writing exams so they can prepare with us. Alright, let's go. So oxidation reduction reaction, so redox reactions. Now remember that for every oxidation there must be a reduction in a redox reaction. So a redox reaction is a reaction whereby oxidation and reduction happen or take place simultaneously. What I mean is, when oxidation takes place, automatically reduction takes place in that equation. In such a reaction, then that reaction is a redox reaction. From the name you can hear redox, reduction and oxidation, redox. Okay, so but we can define oxidation and reduction in three different ways. The first one is addition of oxygen. We say oxidation is the gain of oxygen, while reduction is the loss of oxygen. That's to say, in a species like, let's say, iron oxide combining with carbon monoxide, let's say Fe2O2 plus CO, it will produce Fe plus CO2. Okay, now in that reaction, ion Fe2O2 was reduced to Fe. Why? Because it was Fe2O2, but on the right hand side is now Fe. No O again. Oxygen has been removed, and we said loss of oxygen is reduction. So that means iron oxide was reduced to iron. But on the other side, it was CO. The neighbor of Fe2O2 was CO, and then CO now becomes CO2. It was just one O with one C, but now on the right hand side is one C and two O's. Oxygen has been added, and that's oxidation. That means carbon monoxide was oxidized to carbon dioxide. Okay, so that's one way of defining oxidation and reduction. Oxidation is the gain of oxygen, while reduction is the loss of oxygen. So remember that oxidizing agent is what causes oxidation. So in this case now, carbon monoxide was oxidized. So that means the neighbor, iron oxide, was the oxidizing agent. So a quick way to know is that whatever was standing close to what is oxidized is the oxidizing agent, and that species that is oxidized is the reducing agent, because it's what is going to cause the neighbor to be reduced. Okay, the one that is oxidized is the reducing agent, and the one that is reduced is the oxidizing agent. Okay, all right. Now the second way of defining oxidation and reduction is removal of hydrogen using hydrogen. The first one was oxygen. Oxidation is the loss of hydrogen, while reduction is the gain of hydrogen. Take note, it's the opposite of oxygen now. That's to say, if we have an equation like H2S plus Cl2 to yield HCl plus S, on the left hand side we have H2S and Cl2, but on the right hand side H is now with Cl. So remember, on the left hand side Cl was alone, but now H is with Cl. Hydrogen has been added to it to become hydrochloric acid, and we say the gain of hydrogen is reduction. That means chlorine gas Cl2 was reduced to hydrochloric acid. Go back to the left hand side. Hydrogen sulfide H2S was H2 and S, but the H was then gained by the Cl to form HCl, so the S is now standing alone. Now that means from left to right you have removed H from sulfur, from hydrogen sulfide, and now sulfur is standing alone. That means we can say that hydrogen sulfide was oxidized to sulfur because hydrogen was removed, and we said the loss of hydrogen is oxidation. So that's the second method. And the same way now, since H2S was oxidized to sulfur, that means H2S was what is the species that was oxidized, which makes that H2S the reducing agent. The Cl2 that was reduced to HCl, which is the species that is reduced, the Cl2 becomes the oxidizing agent. It is what caused the H2S to oxidize, and H2S is what caused this Cl2 to be reduced. What causes something to happen is an agent of that thing happening. So oxidizing agent brings about oxidation. It's not the one that is oxidized, while a reducing agent brings about, causes reduction. It is not what is reduced. Okay. Now the third method, which is maybe the most important one, is the removal of electrons. So in this case, oxidation is the loss of electrons, while reduction is the gain of electrons. Always use a shortcut OIL. Oil, O-I-L. Oxidation is loss. Rig, R-I-G. Reduction is gain. To show you that oxidation is loss of electrons, while reduction is gain of electrons. Give an example. We have Cu2 plus Mg to yield Cu plus Mg2 plus. On the left hand side it was Cu2 plus and Mg. On the right hand side the Cu2 plus becomes Cu, no 2 plus again. What happened? The 2 plus left. That means it gained electrons. 2 plus is positive. To become neutral, to become 0 from being positive, you have to gain negative things. Electrons are negative, so it gained 2 electrons and became Cu. No more 2 plus now. So since reduction is gain of electron, then that means copper ion Cu2 plus was reduced to copper metal Cu. Then the Mg on the left hand side goes to the right hand side and becomes Mg2 plus. Is the one that gained that lost that 2 electrons. Mg was neutral here, so for it to become 2 plus, it means it lost 2 negative things and became 2 times more positive than it was. So that 2 plus that Cu had has been transferred to Mg, because it's Mg that gave the Cu the 2 minus. What I'm trying to say is that it's Mg that caused that reduction for Cu2 plus. So that means Mg is the reducing agent. That means Mg is what is going to be oxidized. And you see Mg becomes Mg2 plus, which means it lost electrons. So Mg, manganese, is magnesium becomes oxidized to Mg2 plus, magnesium ions. Now, if you want to, there is a trick to this also. You can always say when the oxidation number is increasing, then that's oxidation. But when the oxidation number is reducing, that's reduction. What I'm saying is, on the left hand side it was Cu2 plus, but on the right hand side is Cu, and Cu is 0. Cu2 plus is plus 2. What happens to the oxidation number? It was reducing from plus 2 to 0. So the trick says that is reduction. So that means Cu2 plus was reduced. And then Mg was neutral, 0. But going to the right hand side it was Mg2 plus. What happened to the oxidation number? It was increasing from 0 to plus 2. So that is oxidation. So you can use that to easily know this rule number 3, removal of electrons, to know which species is oxidized or reduced. But the same thing happens for oxidizing agents and reducing agents. What is oxidized is a reducing agent, and what is reduced is the oxidizing agents. Now let's look at change in oxidation number in detail now. During the process of oxidation, a substance loses electrons and its oxidation number increases in the positive direction, like the case of iron atom. So let's say you have Fe. It will become Fe3 plus by losing electron one by one. First became Fe plus, then moved to Fe2 plus, then Fe3 plus. You see, it's lost electrons and became positive. I want you to understand that aspect. If you are a negative person, for instance, for you to become a positive person, you have to be closer to positive people, right? Or the other way around, you have to lose your negativity. So take that note. For you to become positive, you lose some negativity. So if an ion was like Cu2 plus, means it was 2 times more positive. And let's say it becomes Cu1 plus, it means it's now 1 time more positive. It's losing positivity, which means it is gaining negativity. It gained one negative thing and became one less positive than it was. If it gains another one negative stuff, it will become neutral, 0, because it has dropped from 2 to 1 and now 0. The same way, if it was 2 minus and then becomes 1 minus, it means it has reduced in negativity, which means it has increased in positivity. It was 2 minus, now it is 1 minus. If it gains another positive stuff, it's going to become neutral. So from what I've explained, you see it moved from +2 to +1, then 0. The other one moved from -2 to -1, then 0, by doing 2 opposite things equally. I used in the case of iron. Iron was atom, 0 now, then became +1. That means it lost one negative stuff. Became +2, lost another one, isn't it? Became +3, lost another one, another negative stuff. What is the change in oxidation number of that iron atom? It was 0 before, now it has become 3. As simple as that. The change in oxidation number is that iron has moved from 0 to +3. That is what change in oxidation number is about. Just simple. For you to understand the concept of, is it electrons it's gaining or is it losing? And where was it before it started gaining or losing? Where is it at the final stage of losing or gaining? So that's change in oxidation number. Okay, so you see a question like, what's the change in oxidation number of iodine in the reaction? 5I minus plus 6H plus O3 yields 3I2 plus 3H2O. So they were asking you for iodine, so you go to where you have I. On the left hand side, it was 5I minus. That means -1. Just 1 minus, now it was just minus. So -1. You go to the right hand side, the place you have iodine is now 3I2. No negative charge, no positive charge. That means it's 0. On the left hand side, it was minus. On the right hand side is 0. So that means the oxidation number of iodine changed from -1 to 0. Okay, that's change in oxidation number. Now we move to electrolysis. You know, electrolysis is the process in which certain solutions, certain compounds in their molten forms are broken down, are decomposed into their component parts by passing electricity through such compounds in molten state. So that molten substance, that solution, is what is called an electrolyte. Okay, electrolytes conduct electricity. That's why it's possible for us to separate the component parts, because the positive ions will attract to the negative terminal, while the negative ions will attract to the positive terminal. Okay, so a non-electrolytes are solutions or organic substances which produces molecules instead of ions, so they are poor conductors of electricity. Electrolytes have ions. Ions are what moves. When ions are mobile, then electricity is formed. Okay, so but substances which do not have ions instead have molecules are non-electrolytes. Examples: sugar is a non-electrolyte. Sugar will not conduct electricity. Ethanol is a non-electrolyte. It will not conduct electricity. These are exam questions. Give examples of non-electrolytes. Sugar, ethanol, urea, glycerin, starch, and some others. But that will be okay for WAEC or JAMB or NECO. Now, electrodes are conductors of electricity. The terminals I was calling, they are actually called electrodes. Okay, we have two types of electrodes, the negative electrode and the positive electrode. The positive electrode is the anode, while the negative electrode is the cathode. It's called anode because the negative ions, anions, will be moving to a positive electrode. So the positive electrode is not cathode, is anode, because the negative ions are going to move to a positive electrode, positive conductor. So it's called anode so that you know that anions will be moving to it. In fact, we can call anode anions electrode and call cathode cations electrode. Cations are positive, but cathode is negative. Because a positive ion should come to a negative electrode, then we call this electrode cations electrode, cathode. Since cations are positive, you should already know that cathode should be negative. All right. So since we say electrodes conduct electricity, then we should already know that electrodes should be made of metals or graphite if it's a non-metal. Okay. Now, the assembly of two electrodes in an electrolyte is called electrolytic cell. All right. Now, electrolysis is based on the Arrhenius ionic theory, which states that certain substances produce freely moving ions when they dissolve in water, and these ions conduct electric current in solutions. So when electrolytes dissolve in water, they produce ions, but to varying extents. Strong electrolytes are the ones that will dissolve completely into ions, while the weak electrolytes will not dissolve completely into ions. So it will have a small percentage of ions compared to the strong electrolytes. Okay. So what are the key points in the ionic theory? Number one, the process of splitting the compounds into ions is called ionization. Number two, the fractions of the total number of molecules present in solutions to that of the ions is known as degree of ionization. I'll explain them first and second now. When you put a compound into water, the compounds have to change its states, release the ions that was in solid form into the water. So that is what is called ionization. Now, these ions, we said, will not ionize to the same extent or different compounds. So if a particular compound, 80% of the ions that was in solid form has gone into solution, okay, then the percentage, the fraction of the number of the ions that are still in the locked form, in the solid form, to that is in the water, that's 20 to 80, is what we call degree of ionization. So the extent to which it ionizes. Okay. And the third one, the splitting of the substance into positively and negatively charged ions in aqueous solution is called dissociation. And then ions present in solutions constantly reunite to form neutral molecules. So the first one is ionization. The solid or locked versions of the ions are now released into the water and they are moving. Then we said the degree of ionization is how far does it release its ions into the water. Now, these ions are made of positive and negative, but they are mixed together. Splitting them into positive and negatives. Positive go to this cathode, negative go to this cathode, electrode, is what we call dissociation. All right, so there's ionization, which is the solid ions that was locked in place have been released into water because you have dissolved that stuff in water, compound in water, but the ions are still mixed together. Then dissociation is these ions that were positive and negative mixed together have been separated to positive and negative differently. That's dissociation. Okay, and these ions that are in water will go to meet the rod or the electrode and unite with the ones on the electrode, and the ones on the electrode will go into solution and meet the ones on the in the solution, and it will keep cycling like that. That's what it means. Ions present in solutions constantly reunite to form neutral molecules. It goes to the metal on the electrode and form a molecule, an atom there. Then the one on the atom sees a space in the solution and comes down like that. It keeps cycling like that. Okay. Now there is a preferential discharge of ions. This is in the lecture playlist. You can listen to full lectures, but we're revising. But this is what I mean. An electrode will not, let's say you have 3 types of ions present in the solution, and all these 3 were supposed to go to one particular electrode. That electrode will not dissociate all 3 ions immediately. It will tend to dissociate one and leave the other 2. That's what we call preferential discharge of ions. So how does it decide which one to dissociate or not? Okay. Number 1, the position of ions in the electrochemical series. What I mean is, the cation in a lower position in the series will be preferentially discharged. So if you look at the electrochemical series, you see the cations. We have from the highest position to the lowest position: potassium, sodium, magnesium, aluminum, zinc, iron, tin, lead, hydrogen, copper, mercury, silver, and gold. So gold is the lowest, potassium was the highest. But it's saying the cation, these ones I've read, with a lower position in the series will be preferentially discharged. So if in that solution there was potassium and there was aluminum going to the same electrode to be discharged, that electrode will discharge aluminum because aluminum is lower in the series. That's rule 1. But if it's the anions, the anion in a higher position in the series will be preferentially discharged. So I'm going to read the anions too, from highest to lowest in the electrochemical series. We have fluorine ion, sulfate ion, nitrate ion, chloride ion, bromide, iodide, and then hydroxide. That means F, fluorine, fluoride ion is higher in the series than others, and hydroxide is the lowest here. So if hydroxide was in a solution with fluoride ions and they were going to the same electrode to be discharged, the electrode is going to discharge fluoride ions because the anion in the higher position in the series will be preferentially discharged. That's first, not one way that the electrodes decide which ion to discharge. The second one is the concentration of the ions in the electrolyte. In the water, which one has a higher concentration? Remember I said if potassium, which is higher in the series, is comparing with aluminum, and we know for rule 1, aluminum should have been discharged because the cation with a lower series, the lower position in the series, like aluminum is lower than potassium, would have been discharged. But if in that solution, the amount of potassium in that electrolyte, in that solution, is more than aluminum, then it's going to discharge potassium, even when it contradicts rule 1, because rule 1 says that the concentration of the ions in the electrolyte can also affect the preferential discharge. That's to say, let's say if I really wanted potassium, but I know in this solution naturally is aluminum that would want to be discharged. How do I make potassium discharged instead? I'll add more potassium to that solution. The electrode sees that the concentration of potassium is more than the aluminum, and it says, oh, I would have discharged aluminum, but the percentage of potassium is more, so I have to follow rule 2. I need to discharge my potassium and I get what I want. That's how we can use these rules and manipulate the electrolysis process to have what we actually want instead of what naturally should come out. Okay, that's the second second way the electrode decides what to discharge. The third one is the nature of the electrodes. This one is like some electrodes prefer some kind of metals to other metals. Let's say you are somebody who likes rice, and then you see a lot of food come to you, maybe in an occasion, or you go to buy food and they give you options, you're going to choose rice because you love rice. Some electrodes are like that. Even if they are normally supposed to discharge according to rule 1, the one in the higher series if it's anions, or the lowest in the series, or lower in the series if it's a cation, it won't follow that. It won't even follow the concentration of the ions in the electrolyte. It will then go and follow the one I like. So certain electrodes are like that. Like mercury electrode will, sodium electrode. Mercury electrode, will have a high affinity for sodium. So if sodium was in that solution, even when for rule 1 and 2 it was not supposed to be discharged, sodium will be discharged because mercury loves sodium. Okay, that's the nature of the electrode. It's what it has a higher affinity for is what it will discharge first. So those are the 3 ways that the electrode decides what to discharge first. That's under preferential discharge of ions. So WAEC or NECO will ask you, state the factors that affect the preferential discharge, or the conditions for the preferential discharge of ions in an electrode. Say number 1, position of ions in the electrochemical series. And they can go ahead and explain that for cations, a lower cation will be preferentially discharged, but for anions, a higher anion will be preferentially discharged. And then number 2, the concentration of the ions in the electrolytes, you can explain, and then the nature of the electrolytes or the electrodes, you can also explain. Remember Faraday's first law of electrolysis, which says that the mass of an element discharged during electrolysis is directly proportional to the quantity of electricity passing through that solution, passing through it, and it's represented by Q equals to IT, the formula. So if you want to, you can also use M equals to ZIT, where Z is a constant with a value 3.3 times 10 raised to power minus 4, or you'll be given that value in your equations to use and solve. And then the second law of electrolysis states that when the same quantity of electricity is passed through different electrolytes, the relative number of moles of elements that will be discharged are inversely proportional to the charges on the ions. Okay? What this directly means is that, let's say you had Cu2 plus was supposed to be discharged. So Cu2 plus will have to lose 2 electrons to become an atom, Cu, because it has 2 positive. It has to lose 2, it has to gain 2 negative to become neutral. Now, 1 mole of electron it gains is equal to 96,500 coulombs. So if it had to gain 2, then it needs 2 times 96,500 coulombs charge. Okay, so you see how it's proportional to the charge on the ions. 2 plus, then 2 times 96,500 coulombs. That's how you're going to use it to solve and have your amount of substance discharged. Right? Now we move to electrode potential. Now, when a metal is dipped into a solution of its own salt, we will have that the reduced form of that metal and the oxidized form of the metal come together. They come in contact. Like if zinc, which is a zinc metal, a zinc rod, is dipped into a solution of zinc sulfate, its own salt, zinc sulfate, we'll have 2 possible tendencies. Number 1, the zinc ions in the solutions near the rod will draw electrons from the neutral zinc atoms in the rod and become reduced and deposited as neutral zinc atoms. Or number 2, we'll have that the neutral zinc atoms in the rod will go into solutions as zinc ions and leave 2 electrons behind on the metal rod. Those are the 2 tendencies we have. And due to these tendencies, there will exist a double layer of positive zinc ions and the electrolyte and the electrons on the rod, that's the electrode. Okay? Because of this, a potential difference will exist across this layer. Okay? This is what we call electrode potential. Okay? And it depends on the number of electrons on the valence shell. So the tendency of a metal to go into solution as ion depends on the relative ease with which electrons can be removed from it, that's ionization potential, and on the available energy when these ions are hydrated. Okay, so the more electropositive a metal is, that's high ionization potential, then the greater the tendency to go into solution as ions. So that means oppositely, a less electropositive metal like copper in a solution of its own salt will have its ions more likely to acquire electrons from its rod and become reduced rather than being oxidized. Okay, so the concentration of Cu2 plus in that solution is less because but the concentration of electrons on the rod will be lesser compared to the solution. Okay, so we have a standard electrode. Hydrogen is the standard electrode, is given the value of 1. So other electrodes will be used to compare with the standard electrode, hydrogen. So it's called standard hydrogen electrode most times. Now this comparison has been made already, and then you have a table of the comparisons. You have the different electrode potentials of the different metals. So you won't be asked to do that practically, but you may be asked some questions. You go to the lecture playlist in this channel and you will see electrolysis as a topic. You listen to it or watch it and understand the topic fully. But the different standard electrode potentials of the different metals are already known in a table. So if you are given a question, you will be likely given those values for you to use in solving them. So we move to electrochemical cells. It's a device or a cell which converts chemical energy to electrical energy, because you already know that. So an electrochemical cell that converts the chemical energy of a spontaneous redox reactions into electrical energy is known as a galvanic or voltaic cell. It achieves this by harnessing the energy produced by the redox reaction that occurs within that cell. Okay, so we have the oxidation half cell reaction in that cell, and then the reduction half cell reaction. This is going to be useful in balancing redox reaction. Let's go ahead. We know oxidation occurs at the anode and reduction at the cathode, oil ring. Okay, so electrons always flow from the anode to the cathode. Now, what are the differences? Okay, I'm talking about the electrodes. In an electrochemical cell, the negative electrode is the anode, while the positive electrode is the cathode. Okay, then we have a salt bridge. It is a tube filled with weak electrolytes which serves as a connection between the oxidation half cell and the reduction half cell in a galvanic cell. Okay, so its purpose is to keep the electrochemical reactions from reaching equilibrium too quickly. That's an important answer to a question WAEC or JAMB or NECO will give to you. So its purpose, the purpose of a salt bridge, is to keep the electrochemical reaction from reaching equilibrium too quickly. Also, it connects the two. It completes the circuit. You can put it that way. So there are two now. It serves as you can just say it completes the circuit. Without it, there will be no connection. So it connects the two half cells, but then its purpose is also to keep the electrochemical reactions from reaching equilibrium too fast. Okay, now there are many possible galvanic cells, so we have shorthand notations to describe or provide information about the various species involved in the reaction. So when you see a stroke, one stroke, it means phase boundary from ions to that's from aqueous solution, aqueous to atom. When it is neutral, it is in the atomic form, metal form, or when it's in solution, it's in its aqueous form. So you'll be seeing solid and aqueous. That's phase differences. So in between that solid and aqueous, you'll see a one stroke that shows the phase boundary. And then two strokes shows salt bridge. So two strokes shows what? The salt bridge. Okay. All right. So you can use the values you have here to calculate for EMF, but if you are going to use the cathode and the anode to find the EMF, then EMF will be E of cathode minus E of anode. Okay, cathode is always written to the right and anode to the left, so it can also be E right minus E left. Okay, now we take note of this, that when a cell has a positive EMF, the system is spontaneous, but if it is negative, then the system is not spontaneous, non-spontaneous. That means that the anode will not be able to reduce the cathode if it's not spontaneous. All right, now let's look at the types of electrochemical cells. We have primary and the secondary cells, and what are their differences. Primary cells cannot be recharged, while secondary cells can be recharged. So your rechargeable batteries are secondary cells. The non-rechargeable batteries are primary cells, like your dry cell batteries, your clock batteries, your button batteries, your different batteries that you can recharge. Those are examples of primary cells. The examples of secondary cells are like your phone battery, car battery, rechargeable lamp battery, okay, and so on. All right, another one is that primary cells do not last long, of course, because when the current finishes, you throw it away, it dies. But your phone battery, you've used it for up to 1 year, 2 years, the battery is still the same battery you're using, as long as you didn't spoil it, so it lasts longer because you can recharge it. Okay, and the third one is that, or the next one is that reactions are irreversible in primary cells. That's why you can't charge it, but reversible in secondary cells. Okay, when it finishes, you can refill it. Reversible reaction. Okay, now we look at details of the Daniell cell, the Leclanché cell, the lead accumulator. There are some important things there. In Daniell cell, the Daniell cell consists of a copper vessel filled with saturated solution of copper 2-tetraoxosulfate 6 with a porous pot filled with zinc tetraoxosulfate 6 solution. So the initial EMF produced by the Daniell cell is about 1.1 volts, and this cell has to be replaced once the chemicals in it are depleted. Now in the Leclanché cell, the anode and the cathode are a zinc rod and a carbon rod respectively. So cathode zinc, anode carbon. When we say carbon, we know the only allotrope of carbon that can conduct electricity is graphite. So when they say carbon, they are saying graphite, not diamond, not any other thing. Carbon to electrolysis or electricity means graphite, because graphite is the only allotrope of carbon that conducts electricity. And remember, when you're talking of electrode, you're looking for conductors, things that conduct electricity. Okay, so that's why we say mostly metals, but if it's not a non-metal, then it has to be, if it's not a metal, it has to be graphite. So in the Leclanché cell, we have the cathode being zinc rod and the anode being graphite, carbon. Okay, the electrolyte is an ammonium chloride solution in the wet cell, but if it's in the dry cell, it's ammonium chloride paste. So the Leclanché dry cell is the most common cell used in many small electrical appliances like torches, radios, bicycles, and lamps. But take note of this: the function of the manganese 4 oxide in Leclanché cell is to prevent polarization. This is a JAMB question or WAEC objective questions. The function of the manganese 4 oxide in Leclanché cell is to prevent polarization in the cell. That's a depolarizer. So manganese 4 oxide is a depolarizer in the Leclanché cell. Then the lead accumulator cell is commonly used as a car battery. It is a secondary or storage cell because it must be charged by passing a direct current through it. Now the cathode is of a fully charged lead accumulator is lead 4 oxide, and the anode is metallic lead. The electrolyte is dilute sulfuric acid H2SO4 solution, and when the two electrodes of a lead accumulator are connected to an external circuit, it will produce electricity by discharging. Okay, Now, what are conductors and insulators? You already know this, that substances which conduct electricity are called conductors. And they are of two types. We have metallic conductors, that's the metal wires, graphites, mercury, metals. Then we have electrolytic conductors, that's the electrolyte. These ones are in liquid form, molten state. Okay, like fused lead-2 bromide, sodium chloride solution, dilute hydrochloric acid, and so on. But take note that non-conductors are insulators. Okay, so they are substances that do not conduct electricity. Okay, it is either they are pure solids, that's non-metals. Pure solids don't have ions in them, or they are liquids and non-electrolytes. All right. So how do you balance redox reactions? First, I'm going to give you the points here, but you go to the lecture playlist, you will see a full detailed lecture on balancing redox reactions with examples, and you will understand perfectly. But this is the overview. So you first write down the oxidizing agent and the reducing agent from the equation you'll be given, and then you write the half equations, equation for oxidation and equation for reduction. Write them out differently. Then balance the atoms. You may start from one of the half equations and balance the atoms. How do you balance the atoms? By adding appropriate numerical coefficients. Balancing the number of atoms by adding the correct number of H plus and H2O to the correct or appropriate sides of the equation. Then when you finish balancing the atoms, you balance the charges. Then next point, you make sure that the electron lost in the oxidation half equation is balanced by the electron gain in the reduction half equation. You understand that when you visit the lecture playlist and choose electrode balancing redox reactions or redox reactions as a topic. And lastly, you combine the half equations to get the overall redox equations. When you do that, you'll be able to balance redox reactions, and mostly in acidic medium is what your questions will give you. Okay, so I've already done alkanols in the SS1 video, I think. Yes, it is in one of the revision videos. I've finished that already, no need going into that again. So with this, we've concluded SS1 and SS2 topics in chemistry. The next set of videos will be having SS3 chemistry revision questions. Stay tuned, and you'll get value for following or subscribing to this channel. Thank you. God bless you.